Welcome to Math 21 discussion video on local linear approximation, differentials, and marginals. First, let's go through our outline for this discussion video. We have review of important formulas, local linear approximation problems, differentials problems, and marginals problems. So first, let's go to the review of important formulas. Here they are. First one is the local linear approximation of a function f of x at x is x naught. We call that L of x, and it's equal to f of x naught plus f prime of x naught times x minus x naught. Next, let's assume that we have a function y equals f of x that is differentiable at x. Then, the differential dy of the dependent variable y associated with x is given by the formula dy equals f prime of x dx. Here, dx is the same as the delta of x, or the change in x. And finally, for marginals, we have named the functions c of x to be the cost function, r of x the revenue function, p of x the profit function, and small p of x to be the price demand function. Then we have the following formulas. The profit function, p of x, is the revenue function, r of x, minus c of x. Also, the revenue function, r of x, is x times p of x. So, the number x sold times p of x, the price per unit sold. And finally, if you see marginal before cost, revenue, or profit, that means take the derivative. In other words, for example, if you see marginal cost, that is c prime of x, and so on. So with that said, you may pause the video first and or take a screenshot. We will be using these formulas for our discussion problems. So I'll give you 5 seconds. Okay, now let's go to some local linear approximation problems. For these problems, all you have to do, for the most part, is to apply the formula a while ago. This first formula here. So now let's dive into some problems. Let's have this problem from page 177, A2 of the module. Find the local linear approximation of f of x equals tan inverse of square root of x at x naught equals 1. You can pause the video at this point if you want to solve the problem on your own, and then come back later, resume the video if you want to look at the solution. So I'll give you that time now. I will continue in 5 seconds. Okay, let's show the solution. First, remember that the local linear approximation requires that we take the derivative. So let's first take the derivative f prime of x. So f prime of x is flashed here on the screen. We use the chain rule, noting that the derivative of tan inverse is 1 over 1 plus x squared. So that explains the first term here, 1 over 1 plus square root of x quantity squared. And then we use the chain rule, take the derivative of square root of x, which is 1 over 2 square root of x. And then the rightmost side of the equation is obtained by combining these two fractions. So we have f prime of x, 1 over 2 times 1 plus x times square root of x. Okay, what else do we need? We have f prime x, we have f of x, and we have x naught. So we can already plug into the formula for L of x, which is shown here. So all we have to do now is to substitute x naught equals 1 into both f of x and f prime x, and then plug in the resulting values to get L of x. Okay, let's do that now. At x naught equals 1, we will have L of x is equal to, substitute x naught equals 1, so f of 1 plus f prime of 1 times x minus 1. And then let's just evaluate these values. So f of 1 is tan inverse of square root of 1. And then f prime of 1 is 1 over 2 times 1 plus 1 times square root of 1. And x minus 1 is still x minus 1. Okay, what's the final step? Final step is just to evaluate that tan inverse of square root of 1 and to simplify that fraction. So we have tan inverse of square root of 1 is tan inverse of 1 or pi over 4, and 1 over 2 times 1 plus 1 times square root of 1 is 1/4. So with that said, the local linear approximation is pi over 4 plus 1/4 times the quantity x minus 1. So notice that for the most part, all we have to do to obtain the local linear approximation is, if you're given already the function and the point, you just have to take the derivative and then you substitute the x naught and plug everything into the equation for local linear approximation. The equation in blue in this slide. Okay, let's have a few moments to digest all that's happened. Ready? Let's go to the next problem. Page 176, B1 of the module. Approximate 2.001 raised to the fifth using local linear approximation. So if you want to solve the problem without looking at the solution first, you may pause the video now. I'll give you 5 seconds. First of all, we're not given the function this time, unlike the previous problem. So we will make up our own function. And what's a good candidate here? A good candidate is x to the fifth. So now, let's let f of x be x to the fifth. We want to approximate 2.001 to the fifth, which is f of 2.001. We already have the function. And what is our x naught? We can choose x naught to be 2, the closest integer to the number. So let x naught be 2. And so delta x, the change in x, is the difference, 0.001. Okay, we already have f and x naught. Therefore, we can apply the formula for the local linear approximation. And that's what we're going to do now. So first of all, we need to get f prime. But f prime of x is just 5x to the fourth. So we have f prime, and x naught. So now we can approximate. So f of 2.001 is approximately equal to its local linear approximation, which is given here. F of 2 plus f prime of 2 times delta x or dx, which is 0.001. And all that's left to do is to evaluate f of 2 and f prime of 2. So f of 2 is 2 to the fifth. F prime of 2 is 5 times 2 to the fourth, and then times 0.001. And finally, let's just simplify this expression. So 2 to the fifth is 32, and 5 times 2 to the fourth is 80. Then we multiply 0.001, so you get 32 plus 0.08 or 32.08. And that's the final answer. So let's take a moment to digest the solution first. Let's move on to the next problem. Problem page 176, B2. Approximate 2.99 square root of 3.99 using local linear approximation. Again, if you want to solve the problem first without looking at the solution, pause the video now. I'll give you 5 seconds. Okay, once again, just like with the previous problem, we don't have a function, but we can just make one up here. Notice that the expression is 2.99 square root of 3.99. So what's a good candidate function here? That's right. We can choose f of x to be x minus 1 times square root of x. And then our x naught will be the closest integer to 3.99, which is 4. F of x is x minus 1 times square root of x, but let's expand and express each exponent as a fraction. So we have f of x is also x raised to 3 halves minus x raised to 1 half. We want to approximate f of 3.99. And x naught is 4 because that's the closest integer to 3.99. So our delta x will be 3.99 minus 4, which is negative 0.01. So we now have our function, our x naught, and our delta x. So now we can use local linear approximation, and let's get f prime. F prime of x is 3 halves x to the 1 half minus 1 half x to the minus 1 half. It's easier to evaluate f prime of x using this second expression. That is why I expanded the expression. So now we have f, x naught, and f prime. Let's apply local linear approximation. F of 3.99, which is 2.99 square root of 3.99, is approximately equal to the local linear approximation, which is f of 4 plus f prime of 4 times delta x, which is negative 0.01. So let's evaluate f of 4 and f prime of 4. F of 4 is 4 minus 1 times square root of 4, and f prime of 4 is this expression. 3 halves times 4 raised to 1 half minus 1 half times 4 raised to minus 1 half. I don't mind the 2 plus signs. That's just 1. And then times negative 0.01. And then let's just evaluate. 4 minus 1 times square root of 4 is 6. And 3 halves times 4 raised to 1 half minus 1 half times 4 raised to minus 1 half is 11 fourths. So the expression becomes 6 plus 11 fourths times negative 0.01, which is 6 minus 0.0275 in decimal form, which is 5.9725. So that is the final answer. Let's take a moment to digest the solution. Okay, let's move on to the next problem. Page 176, B3, approximate e raised to 0.01 plus 0.01 ln 1.02 using local linear approximation. If you want to solve the problem without looking at the solution, you may pause the video now. I'll give you 5 seconds. Once again, just like the previous problem, we don't have a function here to approximate. So we will make one up using the expression here. So what's a good candidate function? That's right. A good candidate function is e to the x plus x ln of 1 plus 2x. Then, we want to approximate f of 0.01. What is the closest integer to 0.01? That's 0. So, we let x not be 0. So, delta x will be 0.01. Now, let's get f prime x, which is shown here. E to the x plus ln of 1 plus 2x plus 2x over 1 plus 2x. These last two expressions are obtained from the product rule when you take the derivative of x ln of 1 plus 2x. So now we have f of x, f prime x, and x naught. We can apply the local linear approximation to get f of 0.01 is equal to f of 0 plus f prime 0 times 0.01, which is equal to e raised to 0 plus 0 times ln of 1 plus 2 times 0 plus f prime 0, which is e raised to 0 plus ln of 1 plus 2 times 0 plus 2 times 0 over 1 plus 2 times 0 times 0.01. And let's evaluate that. That's 1 plus 1 times 0.01, which is 1.01. So let's take a moment to take in the solution. Let's move on to differentials problems. First one will be page 176, C2 in the module. A metal box in the form of a cube is to have an interior volume of 1000 cm cubed. The 6 sides are to be made of metal 1/2 centimeter thick. If the cost of the metal to be used is 0.20 pesos per cubic centimeter, use differentials to find the approximate cost of the metal to be used in manufacturing of the box. If you want to solve this problem without looking at the solution first, you may pause the video now. I'll give you 5 seconds. Okay, so what is being asked? That's right, it's the approximate cost of the metal to be used. But the cost of the metal is 0.20 per cubic centimeter. In other words, to approximate the cost, we just need to approximate the amount of metal used. But what is the amount of metal used here? It is the difference in the volume of the interior and the volume of the interior plus the sides. First, we need to recall the volume of a cube with side x. Let's call it Vx, and the formula is x cubed. Now, let's get the difference in volume or the differential. The differential in the volume is dV. By the formula for differentials, it is 3x squared dx. So, what is the volume of the metal material? It is delta V. And what is the change in the side? 6 sides are to be made of metal 1/2 centimeter thick. So since each side will be 1/2 centimeter thick, how much will each side change? Imagine the cube. It will change by 2 times 1/2 or 1. So the volume of the metal material is, as I've said a while ago, the difference in the interior volume and the volume of the cube including the metal. But the volume of the cube including the metal is V of 10 plus 1 because 1 is the change in the side length. And then minus V of 10, which is the interior volume, 1000. But what is this? This is delta of V, right? This is delta of V, but what is delta V? It is the change in volume with original side length N, and then the change in length delta X or dx to be 1. So using differentials, delta of V is approximately equal to dV. And then, what is dV again? It is 3x squared dx. So we just plug in x is 10, and then dx is 1. So we have 3 times 10 squared times dx is 1, so 300 times 1 or 300 cm cube. This is the approximate amount of metal. This is just the approximate amount. What do we want again? We want the approximate cost of the metal. So that means we have to multiply 0.20 by 300. So the approximate cost of the metal is 0.20 times 300, which is 60 pesos. And that's it. So let's take a moment to digest the solution first. Let's move on to the next problem. A cylindrical roller is exactly 12 inches long and its diameter is measured as 6 plus minus 0.05 inches. Approximate its volume with an estimate for the error. This is page 176, C3 in the module. If you want to solve the problem without looking at the solution first, you may do so now. I'll give you 5 seconds. Here, we want to use differentials to approximate the error first. Let's recall the formula for the volume of a cylinder with radius r and height 12. So volume of a cylinder with radius r and height 12, that's Vr is equal to 12 pi r squared. Because the volume of a cylinder is pi r squared h and h is 12. So we now have our function. Let's take dv, the differential. dv is 24 pi r dr. Next, our measurement error is plus minus 0.025 because the measurement error of the diameter is 0.05 and the radius is half the diameter. So that explains this part. So absolute value of dr is 0.025. So error in the computed area is given by, remember it's delta V, and our diameter is measured as 6 plus minus 0.05, so our radius will be 3 plus minus 0.025. So we will be computing the error from V3 and we take R equals 3. So absolute value of delta V is approximately absolute value of dV and we just substitute. So R is 3 and then dr is 0.025. So we have 72 pi times 0.025 and that's 1.8 pi. So absolute value of dV is 1.8 pi. Now what is the approximate volume? The propagated error will be at most 1.8 pi. So we will just get V3 plus minus 1.8 pi. That will be our approximate volume. And hence, the approximate volume is 12 pi times 3 squared. We just substituted R equals 3. So this thing is just V3 and then plus minus 1.8 pi or 108 pi plus minus 1.8 pi cubic inches. And that is the final answer. So let's take a moment to take in the solution. Now let's move on to marginals problems. Let's go to this problem, page 177, D2. The price demand equation and the cost function for the production of a certain product are given by x equals 6,000 minus 30p and c of x equals 72,000 plus 60x, respectively, where x is the number of units that can be sold monthly at a price p pesos per piece. A. Determine the marginal cost. B. Determine the revenue function and the break-even points, i.e., the production level when the revenue is equal to the cost. C. Determine R prime of 1,500. D. Find the marginal profit at x is 1,500. If you want to solve this problem without looking at the solution first, you may pause the video now. I'll give you 5 seconds. Let's solve this problem. Let's start with A. So what is the marginal cost? That's right. The marginal cost is the derivative of the cost. It's just C prime of x. But C of x is 72,000 plus 60x. So its derivative should be 60. And we're done. So that's A. What about B? For B, we want to get the break-even point, i.e., where the revenue is equal to the cost. But we don't have the revenue function yet. We only have price demand and cost. But don't worry, we can obtain the revenue function using the price demand equation. So that's what we're going to do first. So we express the price demand equation as a function in terms of x by solving for p in terms of x. So x equals 6,000 minus 30p. That is the price demand equation from a while ago. We will transpose p to the left side and x to the right side. Divide both sides by 30. This gives you p of x is the quantity 6,000 minus x all over 30. What's next? Next one is the revenue function. We can obtain the revenue function by the formula a while ago. R of x is equal to x times p of x, or x times the quantity 6,000 minus x all over 30. And then let's just simplify a bit to get 200x minus x squared over 30. I just distributed x into the numerator of the fraction and separated the two fractions. So that's r of x. Remember, break-even points are the values of x for which r of x is equal to c of x. So let us solve. R of x equals c of x. R of x is 200x minus x squared over 30 equals 72,000 plus 60x. This is a standard quadratic equation, so let's move everything to the right side to get 0 equals x cubed over 30 minus 140x plus 72,000. And at this point, we can always use the quadratic formula. So we have x equals 140 plus minus square root of the square of 140, which is 19,600 minus 4 times 72,000 times 1 over 30 all over 2 over 30. And after a few simplifications, we get 600 and 3,600. So those are the break-even points. Okay, so what about C? For C, we want the marginal revenue function. So we will evaluate first the marginal revenue function, which is r prime of x. And r of x is just here. It's just polynomial, so we can easily evaluate r prime of x, which is 200 minus x over 15. And of course, finally, we can easily get r prime of 1,500 by substituting x is 1,500. So r prime of 1,500 is 200 minus 1,500 over 15, which is 200 minus 100 or 100 pesos. And finally, the marginal profit is p prime of x. So first, let's get p of x. But what is p of x? P of x is r of x minus c of x. And we will just substitute what are r of x and c of x. 200x minus x squared over 30 minus 72,000 plus 60x. And simplifying that gives you negative x squared over 30 plus 140x minus 72,000. So that's the profit function p of x. What about the marginal profit? Marginal profit is p prime of x, and it's obtained by taking the derivative of p of x. So the marginal profit is negative x over 15 plus 140. So finally, what is the marginal profit at x is 1,500? It's p prime 1,500. And p prime of 1,500 is easily obtained by substituting x equals 1,500 into the marginal profit function. So we have p prime 1,500 is equal to negative 1,500 over 15 plus 140 or 40 pesos. Okay, that was a long one. Let's take a longer moment to digest the solution. Okay, so that's all the exercises I wanted to discuss today. So to summarize, today, we learned about how to solve local linear approximation problems, differentials problems, and marginals problems. For local linear approximation, if you're given the function and the number you want to approximate at, you can just plug in everything into the local linear approximation formula, and that's it. Sometimes you're just asked to approximate an expression. In that case, you have to look for the function on your own. For differentials, you also have to look for the function and then apply the formula for differentials to approximate. And finally, for marginals, just remember, if you say marginal something, that means you take the derivative. And revenue is, what's revenue? X times small p of x. And the profit is revenue minus the cost function. That's all I wanted to discuss today. Finally, here are some additional exercises for you. You may take a screenshot. So done. Thank you for attending the class and see you next time.